Up to this point in the class, we have used quantities of charge in many problems, but we've notably not measured them quantitatively in lab. In other words, we haven't taken an object and figured out how many coulombs of charge are on it. This video is really an attempt to show you how you could do that in lab using a 19th century experiment called the Faraday's ice bucket experiment. So here's the setup. We have this inner wire cylinder, which is actually what we call the ice bucket. The outer wire cylinder, its job is to shield the inside from electric fields outside. It's also wired to the ground through the water pipe of the sink that's over here. And we've got this electrometer, which is a really sensitive voltmeter that's going to measure the potential difference between the two cylinders. So what we're basically going to want to do eventually is to stick a charged object into this bucket. Obviously this thing's not charged right now. That is going to cause a difference in voltage across the inner cage and the outer cage. And we can use that eventually to backtrack and figure out just how much charge is on that object. So why does this work? Well, the potential of the outer cylinder, since it's wired to ground, is always 0 volts. The potential of the inner cylinder changes because when we put the charged object in here, let's say it's positive, that's going to cause electrons to move to the inner surface of the inner cylinder to be as close as they can be to this positive charge. That'll leave the outer surface of it with a positive charge and therefore a different potential, whose potential difference from ground we can measure. So how does this all work? Well, one difficulty is we're measuring a potential difference, but we're trying to figure out about charge. Fortunately, we have an equation so far that relates charge to potential difference. I know I didn't put the delta there, but it's often left out of the equation. But when we were talking about capacitors, we found out that for a given potential difference, you got a given charge. And the only thing we needed to know was the capacitance, that capacitor's ability to store charge at any given potential difference. So our task is really going to be to try to find the capacitance of our ice bucket setup and our voltmeter. And then we'll have a constant to convert potential difference into charge. So the ice bucket itself, it kind of looks a lot like, especially with its outer shield, like a capacitor. But it turns out that all of the components involved, the ice bucket, its shield, the meter, they all have capacitance. And we have to find a way to measure that. So one way to do that is to put a known quantity of charge on this giant capacitor that's been discharged, and then figure out what potential difference ends up being across it. Then we could solve for C. The thing that's tricky about that is we haven't really seen how to get a specific quantity of charge. But once again, capacitors can help us. Because if we charge this capacitor to a certain potential difference, then we'll know how much charge is on it. Let's take a look at that. So I don't know if you can see the little orange dot that's between the two clips of these alligator clips. That is a small capacitor. It is rated at 33 picofarads, which is 33 times 10 to the minus 12 farads. What we're going to do is plug that into a power supply, which I've got set for 35 volts. And that'll put a known amount of charge on this capacitor. We'll then hook it up across the Faraday ice pail, measure the voltage on the electrometer, and we'll be able to figure out what the capacitance is. All right, so I've charged my capacitor. We'll say I've given it a charge of Q original, QO. And that will be governed by the known capacitance, CO, times the 35 volts, or VO, that I hooked it across. So that's thing number one. I'm going to now take this charge and give it to the whole system, which we had discharged, by putting our new capacitor in parallel across the electroscope. So capacitors in parallel actually have their capacitances add. It's almost like the opposite of resistors. So for this new setup, I'm going to have my original capacitor plus the unknown capacitance CE, which is for all this stuff in purple. That will be my new capacitance. And the electrometer is going to be giving me a potential difference, which we'll call VE. And that's going to be equal, of course, to the charge on the whole system. But since that all came from this guy, that too is QO. So I'm just going to do some algebra now, and let's get a value for CE, which is what we're going to need if we want to turn this potential difference into whatever charge we're putting in. So let's do some algebra to get CE by itself. We can set them equal to each other. So now we'll be able to determine what the capacitance is of the electrometer. So we've charged our capacitor with a 35 volt potential difference. Let's hook it across the ice bucket and measure the new voltage, and we can start figuring out what the ice bucket's capacitance is. We'll hook one of them up here and one of them up here. And I got 18 volts. Alright, so with that data, we can plug into the equation we derived. We have our 33 picofarad capacitor. We charged it to 35 volts, and the electrometer read 18 volts once we hooked it across the ice bucket. So that gives us a capacitance of the electrometer and ice bucket of 3.11 times 10 to the negative 11th farad. Alright, so we've seen that if we have the capacitance of a capacitor, it lets us look at the potential difference across it and relate it to the charge on that capacitor. Now that we have the capacitance of the ice bucket, we can put charged objects into it and convert the potential difference we see across the ice bucket into the charge on the object. Let's give it a try. I've got my ping pong ball covered in conductive paint. I'll discharge that. Hold it by its thread. And I'm just going to give this one crank. Watch what happens when I bring the ping pong ball close. I don't know if you saw that, but it was attracted because it was neutral and its electrons had an induced charge. And now it's got whatever charge this one ball had. So we'll go over to our Faraday ice bucket and we'll check. First of all, I want to discharge myself. And this thing has a limit of 100 volts. And I actually can't put this inside yet. It's too much for this voltmeter to actually measure. So I'll just sit here and talk for a minute and we'll see if it discharges. And once I can get it in there, it can get a stable reading, we'll calculate just how many extra electrons there are on this thing. After that, I'll do a somewhat cruder demo in a separate video. I'll just rub some rabbit fur on my shirt. We'll charge up the ball that way, and we'll check how many electrons that transferred. So are we ready? Still can't go in there. So I'm going to stop the video at this point. Alright, so remembering that our capacitance of the electrometer and ice bucket is 3.11 times 10 to the negative 11th farads, we can look at the electrometer when I eventually was able to put the sphere in. About 3 minutes after the end of the previous video, it read 84 volts. So at that time, just using the equation Q equals CV, we can put in our capacitance and our 84 volts, and we end up with a charge of 2.61 times 10 to the negative 9th coulombs. And that is the first quantitative charge that we've ever measured in this class. It seems like a very small charge, but just remember the elemental charge is only 1.6 times 10 to the negative 19th coulombs. That's how many coulombs of charge are on each electron. So this ends up being like 16 billion electrons. It's a huge number. 1.63 times 10 to the 10th. So we just have to remember that when we're dealing with observable charges, that means really large amounts of subatomic charges, microscopic charges have moved. We got that 84 volts by charging the sphere with a Wimshurst machine, an electrostatic machine. Let's look at more at the charges you get when you rub cloths together, like we would maybe when we sit down on a chair in the winter. I'm going to rub the rabbit fur to my shirt, and we'll see what kind of charge that could transfer to the sphere. And what I'm going to do now is I'm just going to take the rabbit fur we used from that first electrostatics experiment, move my ID out of the way. I'm just going to rub my chest a little bit. So that should put a charge on the rabbit fur. I'm going to put that all over the ball. And now we'll stick the ball in there. We'll see how many electrons just from that transfer there was. So this is reading minus 15 volts. So it's the opposite charge of what we had before. So minus 15 volts. We'll calculate how many electrons were on the ball just from me rubbing the rabbit fur on my stomach and then touching the rabbit fur to the ball. All right, so we have a set of parallel calculations. Our 15 volts with the same capacitance of the electroscope and ice bucket gives us a charge of 4.665 times 10 to the minus 10th coulombs, smaller than before. So we're left with a number of electrons transferred as to about 2 billion, almost 3 billion actually, electrons, smaller than before. But remember, before we had a positive 84 volts on the pail, now we have a negative 15 volts. So this is representing charges of opposite signs. This is 16 billion electrons lost because it's a positive charge. This is 2 billion electrons gained because it's a negative charge. And it all has to do with what was the object charging it. In this case, the Wimshurst machine, the paddle I touched it to was positive, so the ball got a positive charge. The rabbit fur must have had a negative charge. There's a lot of cool experiments you can do with this setup. I no longer have access to this equipment, so they're on hold for me. But what you saw here today mostly came out of the manual that came with the PASCO electrometer you see here. The Wikipedia page about the Faraday ice pail experiment is really worth a read, and it goes through the other experiments I would like to do, such as comparing charges on the inside and outside of the inner surface, seeing what happens when you touch the charged object to the inside surface. There's a lot more we could do, and I highly recommend that Wikipedia article for further reading. Thank you.